Lesson 3, tangent. The tangent function. Recall our unit circle. Remember that on our unit circle, this is our x and our y value, and that any point on the unit circle, the x value was equal to the cosine of that point, and the y value was the sine of that angle. Oops. So now if we're looking at tangent of x, or of theta, let's make it a theta, is equal to y over x, which on the unit circle means that it's equal to sine over cosine. So if it's sine over cosine, we can take any point on our unit circle and divide the sine value divided by the cosine value and get our tangent function. So at point 0, we have 1 and 0. If tangent is y over x, it becomes 0 over 1 or 0. At pi over 4, it becomes root 2 over 2 over root 2 over 2, which is just 1. At pi over 2, we have 1 over 0, or undefined. At 3 pi over 4, it will again be 1. However, because our x value is negative, this will become negative 1. At pi, we have a tangent function being equal to 0. 5 pi over 4 is positive 1. 3 pi over 2 is undefined. 7 pi over 4 is negative 1, and 2 pi is 0. Let's graph that tangent function now and see what it looks like. So I'm going to break my graph up into pi over 4. This one is pi over 2. I won't label all of those. And we'll go pi, 3 pi over 2, and 2 pi. From our table of values, we know that our graph is going to start at 0 and 0. Actually, let's go back and look at our undefined. Undefined in terms of a graph means that we have a vertical asymptote at that point. So we have vertical asymptotes at pi over 2 and at 3 pi over 2. At pi over 4, we have a y value of 1, so we're up to this point. And so our graph is going to go like this. We could pick values in between pi over 4 and pi over 2 and see that they are larger than 1. And that the closer we get to pi over 2, the larger those values get. Okay, let's move on the other side of pi over 2. If we look at 3 pi over 4, which will be at this spot, at 3 pi over 4 we have a value of negative 1. At pi at 0, at 5 pi over 4, it's up to positive 1. And again, our graph gets close to that asymptote, but doesn't quite touch it, and close to this one, but doesn't quite cross. At 7 pi over 4, we're at negative 1. At 2 pi, we're back at 0, and so our graph is that piece again. And that relationship would just keep repeating as we go through and increase our value of pi. So here's a graph of the tangent function. So it has the following characteristics. Its period is pi. So from this point, and then it starts back up and gets back to 0, there's a period there of pi. The graph has no maximum or minimum values because each section of that extends infinitely up or down. The domain is x cannot be pi over 2, because that's where our asymptotes are, plus n times pi. Well, n times pi will take us from our first asymptote to the second one is pi. If we add another multiple of pi, it would take us to another asymptote. The range is y can be any real number. Vertical asymptotes occur at x equals pi over 2 plus multiples of pi. X-intercepts occur at x equals n times pi, so at any multiple of pi, so at 0, pi, 2 pi, and so on. All right, we can do those same transformations that we looked at with sine and cos with tangent. What we're going to look at today is an application. It says a small plane is flying at a constant altitude of 6,000 meters. So here it is in my triangle, directly towards an observer. So this plane is coming this way, and the distance is changing. So we're just going to call it d. Assume that the ground is flat in the region close to the observer. Determine the relation between the horizontal distance in meters from the observer to the plane and the angle in degrees. So we're looking for some relationship between this angle and this distance. Tangent will give us that relationship. The tangent of theta is equal to opposite, which in this case is d, over the adjacent, which is 6,000. So d then is equal to 6,000 tan theta. And so it's just a function of tangent. Sketch the graph of the function. Okay, so to sketch the graph of the function, what we're going to do is compare this to y equals tan theta. It has a vertical stretch of 6,000. So we're going to multiply our y values by 6,000. So let's look at our tangent graph. So making our axes. I'll move that up a bit. There we go. Okay, now I need to be able to multiply my y values by 6,000. So I'm going to make each of these squares 2,000. And so this will be 4,000, 8,000, 12,000, and negative below the x-axis. The first point on our graph, and I guess we're doing it in degrees, so this is going to be 0. Let's put 45, let's make this 90, 45, and 90. I know that my tangent function starts at 0, 0, and at 45 degrees it becomes 1. So 0, 0 is unaffected by any stretch. At 1, I'm now multiplying. At 45 degrees, my y value is 1, but I need to multiply that by 6,000, and so it's going to move up here to 6,000. Just like at negative 45, it's going to move down to 6,000. My tangent function has asymptotes at 90 as well as at negative 90, and so that graph is going to look like this. Part C asks where are the asymptotes located on this graph. So our asymptotes are located at negative 90 and at 90. What do they represent? Well, when this angle theta becomes 90 degrees, our picture now would look like this, which is no longer a triangle, and so our relationship would no longer be defined. Explain what happens when the angle is equal to 0 degrees. So when it's equal to 0, again, when it's equal to 0, that angle would be straight up and down, again, not making a triangle, and therefore doesn't make a lot of sense in terms of our model.